Everything's all good. Well, aloha there. And we're going back to the Victorian era again. We're going to skim through. Let's go with. I've already gone through that. Mathematics, science, professional scientism, race of discovery and rate of progress, mathematics, statistics, theoretical, natural history, electrical magnetism, and electrification. Well, let's go back to the professionalism of science. Founded in 1799 with the state purpose of diffusing the knowledge and facilitating the general introduction of useful mechanical inventions and improvements, and for teaching by courses of philosophical lectures and experiments the application of science to the common purposes of life. The Royal Institution was a proper scientific institution with laboratories, a lecture hall, libraries, and offices. In its first years, the institution was dedicated for the improvement of agriculture using chemistry, prompted by trade restrictions with Europe. Such practical concerns continued through the next 2 centuries. However, it soon became apparent that additional funding that was required in order for the institution to continue. Some well-known experts were hired as lecturers and researchers. The most successful of them all was Sir Humphrey Davy, whose lectures concerned a myriad of topics and were so popular that the original practical purpose of the institution faded away. It became increasingly dominated by research in basic science. Painting of the Royal Institution by Thomas Hounsfer Shepherd, circa 1838. And just looks like a typical ancient Greek Roman type of building. Maybe they should have actually painted it like they actually did back then, but people probably didn't because they want to get why it's like that. The professionalism of science began in the aftermath of the French Revolution and soon spread to the parts of the continent, including the German lands. It was slow to reach Britain. However, Master of Trinity College William Whewell coined the term scientist in 1833 to describe the new professional breed, specialists and experts studying that was still commonly known as natural philosophy. In 1840, Whewell wrote that we need very much a name to describe the cultivator of science in general. It should incline to call him a scientist. The new term signaled the recognition of the importance of empiricism and inductive reasoning, but this term was slow to catch on, as the biologist Thomas Huxley indicated in 1852. The prospect of earning a decent living as a scientist remained remote despite the prestige of the occupation. It was possible for the scientists to earn praise but not pudding, he wrote. I just have to say it because of the word pudding. Or puddling. No, it's just pudding. Since its birth, the Royal Society of London had been a club of generally amateurs, though some of whom were the very best in their fields. People like Charles Darwin and James Prescott Joule. Charles Darwin was an amateur scientist, after all. But the society reformed itself in the 1830s and 1840s. By 1847, it only admitted the new breed of professionals. The Victorians were impressed by science and progress and felt that they would improve society in the same way as they were improving technology. Britain was the leading world century for advancing engineering and technology. Its engineering firms were in worldwide demand for designing and constructing railways. Ease of discovery and rate of progress. A necessary part of understanding scientific progress is the ease of scientific discovery. In many cases, from planetary science to mammalian biology, the ease of discovery since the 1700s and 1800s can be fitted to an exponentially decaying curve, but the rate of progress is also dependent on other factors such as the number of researchers, the level of funding, the advances in technology. Thus, the number of new species of mammals discovered between the late 1700s and late 1800s grew exponentially before leveling off in the 1900s. The general shape is known as the logistic curve. In other cases, a branch of studded reaching the point of saturation. For instance, the last major internal human organ, the parathyroid gland, was discovered in 1880 by Ivar Victor Sandstrom. Sandstrom. This does not mean the basic science was coming to an end. Despite the despondency of the many Victorian era scientists who thought that all the remaining was measuring quantities to the next decimal place, and that new discoveries would not change the contemporary scientific paradigm. Yeah, it's paradigm. Huh. I didn't know that's how you spelled that, paradigm. As the 19th century became the 12th, science witnessed truly revolutionary discoveries such as radioactivity. The basic science continued its advance through a number of 12th century scientists shared the new pessimism as their late Victorian counterparts. So pretty much the idea of the scientist itself is gain prominent, a standard education for scientists to learn more educational studies, to study more of the natural science and other science, hardcore scientists. And yeah. Mathematics and statistics. All right, let's see how this goes. Nightingale's morality charts from the Crimean War using a form. Wow. A type of a form of a pie chart that works as a graph. In the field of statistics, the 19th century saw significant innovations in data visualization. Let's go. Create charts of all sorts. Justified is thus a man who has carefully investigated a printed table finds, when done, that he has only a very faint and partial idea of what he has read. End quote. Then let's go with Florence Nightingale drew the first pie charts representing the monthly fertility rates of the conflict, distinguishing deaths due to battle wounds in her most section, thus due to infectious disease, and other causes. And yeah, now there's Carl Pearson, who grew them into the name histograms. Pearson used them in the 1895 article Mathematical Analogy of Biological Evolution. One such histogram showed the buttercups with large numbers of petals were rarer. Normal distributions, along with things from Galton. He invented that he was called the quincunx to demonstrate why mixtures of normal and distributions were normal. Galton knows that its main particular trait and the offspring generation differ from those of the parent generation. Alright. But noted that correlation does not imply causation. A phenomenon now known as regression to the mean. So, yeah, this is the beginning of modern day statistics, especially with understanding of a growing population that requires data to understand what's going on, their impact, other factors that are involved with that, much more. So what's up with the lighting here? Not the lighting that's usual, but I believe it's lighting here. Okay, that should be good. Let me see. Alright. That should all be good. Now, alright. During the late 19th century, British statistics introducing number methods to relate and draw conclusions from statistical quantities. Then it goes further than that. In 1828, an essay on the application of mathematical analysis to the theories of electricity and magnetism follows there. I hope they didn't get freaked out when they were selling Frankenstein, how he was born, and how it was inspired by an event where they were trying to bring a person back to life, or at least appear to be by electricity. He goes, oh boy, that did freak a lot of people out. Arthur Cayley is credited with the creation of the theory of matrices, rectangular arrays of the number, rectangular arrays of numbers as distinct objects from the determinants. Okay, so that's what it is. Now let's go with theoretical mechanics and optics. Early contribution study of elastic, how objects behave under stresses, pressures, and loads. And go through the show the light polarization scripts here. Equal partition theorism was a calculation of the ratio of the specific heats of gases. Yeah, I'm still a bit confused with this. I absolutely don't know much about this. So, in the 1860s, James Clerk Maxwell published a series of papers on the subject. Unlike those of his predecessors, who were only using averages, Maxwell's papers were explicitly statistical in nature. Some molecules were moving faster and slower than the average. And the dynamics of rigid bodies as follows. In 1899, the request of the British Association of Advancement of Science from the year is embroiled. Despite its age, it remains a print in the early 21st century. The analytical dynamics of particulars and rigid bodies. Oh, wow. Okay. Thermodynamics, heat engines, and refrigerators. Something I do know more. During the 1830s and 1840s, traditional caloric theory of heat began losing flavor to the dynamic alternatives, which posted that heat is a kind of motion. Breer and amateur scientist James Prescott Joule. We're reading out Prescott Joule. Why do you like to say just amateur? Was one of the proponents of the latter. Joule's intricate experiments, the most successful of which involved heating water and paddle wheels, making full use of his skill in temperature control as a brewer, demonstrated decisively the reality of the mechanical equivalent of heat. Yeah, don't want to dwell much on that, because I gotta talk about thermodynamics to people on the stream, and yeah, it's a lot, especially for me in this time. From the 1930s onwards, refrigerators relied the expansion of compressed air and the evaporation of volatile liquid. Evaporation became the basis of all modern refrigerator designs. Long distance shipping of the perishable foods, such as meat, boomed in the late 1800s. On the theoretical side, new refrigeration techniques were also of great value. Okay, going on that. This paved the way of the development of low temperature physics and the third law of thermodynamics. Now we go to natural history. This study of natural history was most powerfully advanced by Charles Darwin in his theory of evolution, first published in the book On the Origin of Species in 1859. Now let's go here. It talks more about history. Okay, what should I find? Kelvin employed a mathematical model by von Helmholtz, suggesting that the energy of the sun is released via gravitational collapse to calculate the age of the sun to be between 50 and 500 years. He reached comparable figures to the Earth, and the missing ingredient here was the radioactivity, which was not known to science till the end of the 19th century. So understanding how geology around the world would work and the interaction in different environments, to the point that they start understanding that there's more elements in the world that they have not discovered yet, like radioactivity. Now, electricity, magnetism, and electrification, after the Dane Hans Christian Ørsted, demonstrated that it was possible to deflect a magical needle by closing or opening an electric circuit nearby. A deluge of papers attempting to explain the phenomenon was published. Alright. Michael Faraday delivering a Christmas lecture of the Royal Institution. Also understand that Faraday is another. We actually use his name with Faraday cages because of how there's no frequency that come through anything that you want to protect, especially if an electromagnetic pulse comes in. Did I miss any pictures? Just this one, and yeah, so far just that one because I was focused on just going through here talking. William Thomas, knighted by Queen Victoria in 1866 and elevated to Lord Kelvin of Largs in 1892, was one of the top physicists of the day. And that's where he is, just writing his stuff. And where are we here? A transformer. Okay, let's go here. Michael Faraday set himself to the task of exploring the nature of electricity and magnetism by experiments. The first electric motor through is now represented on model one, a transformer not used to step on up the voltage and step down to the current or vice versa, and a dynamo, which contains the basic electrical turbine generators. The practical value of Faraday's research on electricity and magnetism was nothing short of revolutionary. A dynamo converts mechanical energy into the electric current. Okay, yeah, we go further up there. Electrical current, whilst a motor does the reverse. And you could actually see him demonstrating all of that to understand how electricity comes through and how it flows, ebbs and flows. It must be interesting for a person just to, talk, pray for it, and you just see him saying. And yeah, it's just a bunch of people who were just naturally curious because they never see anything like that. And the person was just pretty passionate, passionate to an extent, to share his works to the public, which means that their work can be shown off. And they get a time to feel good of themselves. James Clerk Maxwell simplifies all the known electricity and magnetism into a single mathematical equation. Maxwell's equations. Yes. Heinrich Hertz, after introduced Maxwell's prediction, was confirmed by German physicist Heinrich Hertz. In this process, Hertz generated and detected what are now called radio waves and built crude radio antennas in the predecessors of satellite dishes. Then you had Hedrick Lawrence using suitable boundary conditions. Then there's more about this. Should I go more? Let me read this thoroughly. Okay. Yeah. Electrochemistry. And together with all the scientists here, they come up with the word electroid, anoid, cathode, electrolysis, electrolyte, ion, and cation. I always get that confused. It's tomato. It's a tomato situation. If the chemical elements were distinguishable from one another from simple ratios of mass, and if the same numbers of electricity deposit amounts of these elements upon the poles in ratios, then electricity must also come in the discrete units later named electrons. And then further word. Electrodes inside a vacuumed tube, cathode rays attracted the attention of many physicists. Okay, the experiment enabled Thomson to calculate the radius between the magnitude of the charge and the mass of the particle. Alright. Although the atoms of each chemical element have different numbers of electrons, all electrons are identical. Yeah, that's the understanding of its properties. Is that true now? Is it different? Alright. Let's go with computer science and logic. That is the thing to understand. In the Victorian era, that was the time when the modern world started advancing, like computer science, all the way back then. Before Alan Turing. and his invention of a modern type of computer. Inspired by the exploration abstract algebra of George Peacock and Augustus D. Morgan, George Bully published a book titled Investigation of the Laws of Thought in 1854. And it goes further than that. Boolean, there's mathematical formulas that in fact, it can be traced all the way and back to the Hellenic civilization. While people have devised such machines over the centuries, mathematicians continued to perform calculation by hand, as machines offered a little advantage in speed. For complicated calculations, they employed tables, especially of logarithmic and trigonometric functions, which were computed by hand by the right in the middle of the Industrial Revolution in England. Charles Babbage thought used the all-important steam engine and powered a mathematical computer. The difference engine, unfortunately, Babbage managed to secure government funding to the construction of the machine. The government successfully lost an interest, and Babbage faced considerable troubles developing the necessary machine components. He abandoned the project to pursue a new one, his analytical engine. By 1838, he had worked out the basic design like a modern computer. It consists of two basic parts: one that stores the numbers that could be stored, the store, and one that performed the operations, the mill. Yeah, Babbage adopted much things. In the other case, for computing Bernoulli numbers, she employed what modern computer programmers will recognize as loops and decision steps, and gave detailed diagrams possible the first flow chart ever created. And she notes down more about that. Oh yeah, let me definitely read that because. And also, I want to reread this. I'm gonna read this in a hurry, in my own time, thoroughly, but in a hurry. Yeah, I'm surprised they didn't mention making an algorithm itself. But that's what they looked at when doing calculations, because that was one purpose, to have a computer to make the process of crunching numbers more faster than by hand, by human. Alrighty. On the limits and implications of the computer, she wrote, the analytical engine has no presentations, whatever, to originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relations or truths. In province is to assist us in making available what we were already acquainted with, but it is likely to exert an indirect and prosal influence on science itself in another manner, for in so disturbing and combining the truths and the formulas of analysis, that they may become more easily and rapidly adaptable to the mathematical compositions of the engine, the relations and the nature of the many subjects. And the nature of many subjects in the science are necessarily thrown into new lights and more profoundly investigated. It is, however, pretty evident on general principles that it's devising for mathematical truths a new form in which to record and throw themselves out for actual use. Views are likely to be induced, which should again react to the more theoretical phase of the subject. Alright, now communications and transportation, steamships. Steamships were one of the keys to Britain's prosperity in the 19th century. This technology was persistent in the Victorian era, then during the late 1800s. Okay, yeah, just want to talk about the shipping situation and the fact that Great Britain's been a large naval power, not only the Victorian era, but for some centuries, pretty much almost forever, when it was an empire. Yeah. This is something we don't know. Let me just summarize more. So yeah, commercials, commerce has been a big thing. Later expanded more into India and then to Africa. along with Australia because of it becoming a new colony rising around this time. And then, yeah, the SS Great Eastern was the largest ship built at the time, capable of transporting 4,000 passengers from Britain to Australia without having to refuel along the way. This was also the time when, yeah, people were immigrating to Australia. It's not just a penal colony anymore. The British government had long realized the national prosperity depended on trade. Deployed the Royal Mint to protect maritime trade routes and finance the construction of many steamships. Now, that's the new thing, steamships. Okay, so that's pretty much it. Well, I didn't talk much about steamship, but it seems like that's going to become a prevalent thing later, after Victoria's death. Telegraphy, telephony, the wireless, and photography. Alrighty. The South London Royal Mail traveling by train from Peterborough East, Northamptonshire by James Pollard, 1845. Picture on the British Empire's submarine telegraph cable network eventually connected all of its major possessions. Going through Canada, London to all the way there. And then to here, to Session, to South Africa, into right here. Oh yeah, it's south in the middle that go either India. It has its own channel. Now, although the idea of transmitting messages via electrical signals dated back to the 19th century, 1820s, 1837, I'm looking at the dates, by the mid-1800s, the telegraph cable was later across the English Channel and the Irish Sea and the North Sea, mid-1800s. And that's when this map became true, around the mid-1800s. So, the second period of Victoria's era is separated by 3, and the second one is recognized when Victoria's husband died. So around like the 1859, around the 1860s. In 1876, Alexander Graham Bell patented the telephone. He is the person who first patented it and became famous from it. He's not the first inventor, but he did patent it, and everybody remember him as the person who revolutionized everything by telephone. A little over a decade later, 2000, 26,000 telephones were in service in Britain and 1,500 in America, and had telephones. Multiple switchboards were installed in every major town and city. Oh my god. In America alone, that's a lot. I think with the British Empire, it would have been more because it's people around, but it does seem that with a country that's expanding in its own mainland, it's way different. And also having places that we're looking at stayhoods, like in mainland America versus just colonies, or later even commonwealths, which, yeah, I don't expect that. The shipping industry adopted the technology at once. Radio broadcasting became extremely popular in the 12th century and remains in common use in the early 21st century. The global communication network in the 20th century, such as roots in the Victorian era. Another important innovation in communication were penny block, the first postage stamp, which standardized postage to a flat rate regardless of distance sent. Okay, yeah, that's different. The postage stamp would have been really expensive depending on where you send it. But that just could show how people who mainly use telephones would usually use it for professional reasons, not for recreational reasons like what we do nowadays. But even then, that's just weird to compare a person using a land telephone to contact just one person versus now there's just multi-facet use of a smartphone. Everyday world. It's like augmented reality device. Oh yeah, it's the history of it. And where we left off was railroads. Oh yeah, we got still plenty to do. But you know, I'm still excited about it. But anyhow, that's pretty much it. And aloha.